Today, we're going to tackle a question that sounds like a real paradox. How can computers, these machines built for perfect logic and predictability, create something as chaotic and unpredictable as randomness?
I mean, seriously, think about it for a second. It's a bit of a head scratcher, right? Computers are designed to follow a set of instructions perfectly every single time. Their whole deal is being predictable. And it's the exact opposite of what we think of when we say something is random. In the real world, when you flip a coin or roll a die, that's randomness. It comes from all these tiny, unpredictable physical forces. But a computer, it's all about following a strict, repeatable sequence. It's designed to get rid of all that messy, physical world unpredictability. So how on earth do you get chance out of a machine that's built to destroy chance? Well, this is where things get really clever. See, computer scientists realize that trying to create true, real-world randomness inside a computer is honestly a huge pain. It's slow and complicated, so they came up with an amazing workaround. They decided to simulate it. And the secret ingredient for this whole recipe is a single core random number. And this gets us to a really important idea: pseudo-randomness. The keyword here is pseudo. It means it's not actually random. It's not like pulling a number out of a hat. It's just an algorithm that's so good at generating a sequence of numbers that looks random that for almost everything we do, from video games to picking a random song, it's more than good enough. So how do programmers actually get their hands on this pseudo-randomness? Well, in most programming languages, there's a basic building block, a simple command they can use. In JavaScript, for example, it's called Math.random. You can think of this little guy as the seed from which pretty much all digital chance grows. So what does this command actually do? It just spits out one number, a decimal number that's somewhere between 0 and 1. It can be exactly 0, but it will never ever be exactly 1. It just gets infinitely close. So what we're left with is this tiny, unpredictable decimal, and that's our starting point for everything else. Okay, so a random decimal between 0 and 1 is cool, I guess. But it's not super useful by itself. I mean, you can't roll a 0.73 on a die. So the real magic is taking this raw random decimal and sculpting it into something we can actually use. For our example, let's turn it into the roll of a classic six-sided die. And we're going to do this in 3 simple steps. First, we're going to scale the range to make it bigger. Then we'll chop off the decimal to make it a nice whole number. And finally, we'll just shift the range over a little bit to get exactly what we need. All right, step 1. We take our random number, which is somewhere between 0 and 1, and we just multiply it by 6. Suddenly, our range is way bigger. Instead of a tiny number between 0 and 1, we now have a random decimal somewhere between 0 and, you guessed it, 6. We're getting warmer, but there's still a problem. Dice don't land on 3.1415, They land on whole numbers, integers. So how do we get rid of all these pesky decimals? For that, we've got another handy tool called Math.floor. And it does exactly what it sounds like. It takes any number and just rounds it down to the whole number right below it. It finds the floor. And just like that, all the decimals are gone. We're left with only 6 possible outcomes: 0, 1, 2, 3, 4, or 5. We are so close. This is great. We have 6 possible numbers, which is exactly what a die has. But hang on, our numbers are 0 through 5. A standard die is numbered 1 through 6. We're off by 1. So what's the final brilliant piece of this puzzle? It's actually the simplest thing you can imagine. To get our numbers from the 0 to 5 range into the 1 to 6 range, we just add 1. That's it. And there you have it. This one line of code is the whole magic trick. This is a perfect simulation of a 6-sided die. It takes that random decimal, scales it up, chops off the decimal, and shifts it over, all in one beautiful little package. It's pure chance, built entirely out of predictable logic. So now that we've forged this awesome new tool, let's put it to work. Let's see how something this simple can be used to make decisions. Okay, the most basic example is a coin flip, a classic 50-50 shot. We don't even need our fancy die formula for this. We can just use our original Math.random number. Since it's between 0 and 1, we can just say, hey, if the number is in the bottom half, less than 0.5, we'll call it heads, and if it's in the top half, we'll call it tails. Easy as that. But a coin flip is just the beginning. The real power of this comes when you want to handle a whole bunch of different possible outcomes.
Think about a magic 8 ball. We can use that exact same technique we used for the die to generate a random number, maybe between 1 and, say, 20. Then we just assign a different answer to each number, and suddenly our logical computer is spitting out mysterious fortunes like, reply hazy, ask again, or my sources say no, all driven by that one little pseudo-random number. So now, let's just take a step back and zoom out for a second. Because what we just did, building a simple, useful tool out of a few complicated parts, it actually demonstrates one of the biggest, most important ideas in all of programming. It's called abstraction. Abstraction is basically the art of hiding all the messy details, right? We went through 3 separate steps to make our die roller work. Abstraction says, let's bundle all that hard work up into a neat little package so we never have to think about the complicated stuff ever again. I mean, can you imagine having to type this whole crazy formula out every single time you needed a random number in a game? It would be so annoying, and you'd probably mess it up half the time. With abstraction, we can hide all of that mess behind a single beautiful command. We can create something where we just say, hey computer, give me a random number between this starting point and this ending point. And that's it. All the complicated stuff happens behind the scenes. And that is the big takeaway here. Inside that one simple command is all the logic, all the steps we just spent the last few minutes building. You don't need to know how it works anymore. You just need to know that it works. And that's what makes programming so powerful. So this all brings us to one last big question. We've just seen that the shuffled playlist, the dice roll in your game, it isn't truly random. It's a really, really clever simulation. So it kind of makes you wonder, what else in your digital life, what other things that feel spontaneous and real are actually just another beautiful piece of logic in disguise?